Hello, everyone. Welcome to this week's Crunch seminar. Today we have two talks. The first talk is by Professor Markus J. Buehler, McAfee Professor of Engineering at MIT. His talk is about compositional reasoning and multi-agent systems for discovery and design. Professor Markus J. Buehler is the McAfee Professor of Engineering at MIT and a pioneer in AI-driven knowledge discovery. He created powerful graph-aware multi-agent AI platforms that turn heterogeneous data into science-grounded actionable insight, powering breakthroughs in material science, biology, and healthcare. Professor Buehler is among the world's most cited material scientists and the recipient of numerous honors, including the Feynman Prize, the ASME Drucker Medal, J.R. Rice Medal, and the Washington Award. He is a member of the US National Academy of Engineering. For more than a decade, he has also taught executive and technical professionals at MIT, shaping the next generation of leaders in engineering, knowledge discovery, and artificial intelligence. With this short introduction, I invite Professor Buehler to present his talk.
Yeah, no, thank you so much, Vivek, and really a pleasure to be here today. Yeah, it's very special. I think Brown has pioneered AI and especially science for AI for many years, and glad to share a little bit about our work with you all today. So the talk is titled, so it has to do with compositional reasoning and multi-agent systems, and I will try to cover these topics, and give you an update on what we have done. So feel free to, interrupt any time with urgent questions. Otherwise, of course, at the end we'll have a little bit of time as well. So my interest is, my lab at MIT is really focusing on materials. I also am very interested in creativity, sound in particular. We'll talk about this a little bit later. And especially modeling, but also I like to build things at the same time. And we try to go, if we can, usually from modeling materials, so from the atomistic scale, as you can see, I think here on the right, you can see sort of this atomistic model of a material, collagen in this case, to understand it, synthesize new insights, and then ultimately predicting a new material, maybe make a new discovery, and then creating an actual prototype in the lab. So that's usually what we try to do. So now, in the last few years, we've spent quite a little of effort in going really deep into the question of what does it mean for AI to discover, and that's different, or I would say more challenging than generally talking about AI. AI can mean a lot of different things, but letting a machine actually make discoveries is particularly challenging. So we'll talk a little about that. And we'll make the case, that we need to really still work pretty hard on creating the architectures and frameworks to achieve that goal, in spite of all the progress we've made. I'll show you a little bit of work we've done in that field and how we think we can reach that goal. And also maybe if there's time at the end, we can talk a little about AI in education and sort of thinking about how we, as also as educators or as mentors for new generation of students, how we engage with this topic. And that includes a bunch of different topics, including teaching, of course, but also how research is going to change if AI is able to do research on its own and make discoveries. So the outset, I want to say that, when people are sort of beginning to talk about AI and machines that can think, we always think this is something very new and exciting. It's been sort of imagined in the last few years only, but in fact, it goes back to many centuries ago. And there's early work from the 1700s where humans at the time started thinking about whether they can build a machine, an actual mechanical machine that would model the thinking process. And at the time it was met with bewildered, I think, reception, I guess, and really didn't, in fact, come to any fruition or any kind of real ideas or ideation or prototyping until the 20th century, when we had computers that could actually become sort of realizations of some of this dream. But this dream has been around for a long time. Now, as scientists, we're in 26 now, and I'd like to sort of take a step back. Where are we on this journey of actually creating these machines that can think and discover and create, and hopefully also have agency in the world, so they're not just imagining, they're actually building stuff themselves. So where are we? Well, we have made some really incredible progress in the last 10 years. I mean, everybody remembers AlphaGo, right? The sort of historic moment when the machine beat Go and discovered new moves, right? That wouldn't necessarily be in any kind of manual or training data. And then on the other hand, 25 was a year I think where we saw significant advances in math and AI. DeepMind, OpenAI, there's companies and startups that are getting into this field. I think very exciting sort of developments there. Machines being able to solve extremely difficult math problems. And then you're looking at also maybe benchmarks. You can see here's biology benchmarks or software engineering benchmarks, and you can kind of see they're all being saturated, right? I mean, we invent new benchmarks and then we're saturating them, we train better models. And when you look at this, you might think, well, what's left to do, right? I mean, we're sort of at the end of it. The answer is actually it's not quite like this, I think. I think there's a fundamental difference between something, like a chatbot that can give you answers about things we've already learned, like training a LLM on the entire world's knowledge is really wonderful, and it gives us access to that knowledge, with a couple of lines of maybe query or code. But really what we haven't quite, I think, figured out yet is how do we make the machine actually write the books, not just train on the books we have already written. So how can we create a machine that can make truly new discoveries? And what does this mean? So it means actually, if you think this through, that we're not simply looking at training a model and getting answers. It means that the model, in fact, has to realize that the answer is wrong, and it has to rewire its understanding of the world. That's the point of science, that we discover new facts, new insights, and we change the view of the world. And there's many examples, turning into quantum mechanics and many other areas, right? Where we have to change our world belief, our world model. And that is sort of principally, to me, this is the ultimate frontier of science. Right? So this is where I think we want to build the machine to do this. And this has to do, of course, at the end, you got to think about adaptive intelligence. I think we have to realize that, training a model and then the model sort of gives you an answer is not the answer, right? There has to be something more, where models have an ability to learn and adapt while they're thinking through a problem or solving a problem. So this is one, kind of statement we want to keep in mind. The other one is, I think about data. I think this is something I see more and more discussion on this actually on LinkedIn and X. It's great that, data is, of course, very important, but data is not everything. And especially, two things. One, data is not insight, right? Data can be very confusing. It can just be some basis to train some sort of correlation model. It doesn't actually help us understand things unless we do something special with the data. And the other thing really about data is that a lot of data we're producing is data about things we already know. I mean, biology is a great example. We can collect more and more sequences, but these are all sequences nature has already tested and built. What about the sequences that nature has never explored? Those are the interesting things. So very far out of distribution proteins or chemistries are really questionable. And the same, of course, in operations, manufacturing, and other areas where we have a lot of data, but the edge cases are really what we care about. We care about when the thing doesn't work anymore, right? So I think if you in our group, we've been quite interested in this for a long time, and we think that there's some really fundamental things we need to think about. That one is we want to build some ability in a model, or at least have an incentive for the model to learn deeper abstractions, and we call it reduction here. Right? So the idea that you have a lot of observations. Let's discover a PDE. Okay, and this is amazing work, of course, from Brown that has explored this for many years. Right? So can we maybe discover which PDE governs this phenomenon, and this actually is a very powerful reduction from complexity. And the other side, though, is that we have to build models, machines, algorithms that also compose new things. So it's not enough to just reduce. We also want to say, well, can we create something totally mold breaking? And so here, I think creativity is an example. A lot of science works like this. We think outside the box. Engineers are very creative. Right? They really imagine new things that aren't yet there, but they figure something out that could be there, and then they build the system to make this real. And of course, then there's art. This is an example I use here is mold breaking sort of mechanisms is really the nature of art. Right? You create something that conveys a message, but it really oftentimes breaks the boundary of what we believe to be true. Right? And in art, maybe in composition of music, you have you're combining very different forms of music and breaking the rules literally. And I think, the 20th century we had, rock bands that did that. And then I guess in a couple hundred years ago, we had Beethoven do that. I mean, it's fundamentally creative mold breaking, boundary breaking process. And we're interested in building these types of systems that can do that, right? So they can reduce principles, and then they can rewire the world, and they can actually come up with something new through compositional reasoning. Um, I think compositionality is really important. We want to be able to not only make a prediction, right, and imagine something, we want to be able to understand why it is true or why it's likely true, so we can falsify and verify it. And we want to be able to sort of have a representation of the world that is accurate and traceable and yeah, verifiable, falsifiable. And here's an example that I like to use. I think just for those of you who maybe are saying, well, maybe, why don't we just keep scaling models? And here's an example I think that illustrates very nicely. So if you imagine you go back a couple of decades, or a couple of, not decades, a couple of tens of thousands of years, right? Or maybe even longer. And at some point, humans discovered fire. They basically accidentally came across it and they started using it. And they made food, they cooked food, they warmed themselves, obviously. And so you can say, well, if you were to train an AI, like a large language model, perhaps on that data, like here's all the different ways of making fire, and then you were to say, let's optimize fire, let's make a bigger fire, let's produce more energy, right? And so the model might come up with a better way of burning things, or maybe making a bigger fire, but it wouldn't necessarily come up with fusion. So the way we came up with a fundamentally new way of producing energy is by, well, thinking much more deeply about the world. We realized actually it's not just chemistry. We have sort of more foundational relationships between matter and energy that we can actually bring to bear and unlock millions times more output than what we could ever do with fire, basically, right? And so this is something, if you imagine training this model on all the fires in the world, it's not going to come up with fusion suddenly. And this is sort of the challenge I think we're facing today. We are at the cusp of figuring that out, but I think this is still the frontier to do. And particularly for me, I work in materials, and my own sort of journey in this field. We're just talking about. I've been at MIT for 20 years. An incredible place, incredible people, and I've spent the last 20 years there, in building molecular multi-scale models of mainly biology, some engineering systems. Before that, of course, I was inspired by the work that people did in the 1950s at the national labs in building atom-by-atom models. And, at some point, sort of from, okay, in the 1950s, me coming in, doing a PhD in about 2000 and building models of materials, atom by atom, seeing, kind of the vision of multi-scale, we realized that, okay, I don't want to just model one material. Maybe I want to do something more than that. I want to model you know, many different kinds of materials. Here's an example of the stuff I've been working on, wood, spider silk, blood vessels, motor proteins, right? And kind of ask the question, if we understand how these things work, can we understand more if we compare them to each other and maybe find similarities? So this is sort of the scientific principles. Now, can we find unifying principles? Do we understand the boundary? What's shared? What are the shared operators? Where's the difference? And can we optimize this, and can we actually automate the process? So this is what I became really interested in about 10, now it's actually 12 years ago. I think in 2005, 15, around that time, we started getting into this, asking these sort of more fundamental questions. And it took a long time to actually get to the point where we could build models and especially numerically do that. And this did not happen until a few years ago, right? So amazing examples, of course, for these materials. Unless probably you're all convinced that these biological systems are quite interesting. They're interesting because they have unique properties. Like silk is very, very strong, very, very tough. You got, incredible structures. So my lab, we have We do mainly computational work, but we have some experimental facilities as well. And we actually scanned, this is a scan of a 3D spider web that we've produced. So we're trying to figure out how do we not only use data we have, but also collect new data. And we use this to try to figure out, okay, now that we have a structure of a web, can we go back, to the molecular scale and perhaps understand, what's the origin of things like strength and toughness, um, you know, um, from this multi-scale perspective. Okay, and when you look at these kinds of sorry, who's calling me, but sorry about that. So when you look at these different systems, you want to kind of build relationships with others, and of course you can do this with words. I think words are obviously not the most compressed way of describing it. And so we got into the field of category theory. We built category theoretic formal representations of how materials work. So what is the origin of toughness in silk? What is the origin of toughness in another material? And perhaps can we understand function in a totally different domain like music? Okay, and then ask the question, how do we map them to each other? So this is what we call a functor. So we have functorial isomorphisms. If we can actually identify structural identities, that look similar or maybe have some differences, but they're shared representations or relationships across very different domains. So this is something that we did on sort of pen and paper kind of approaches. And we then sort of got stuck, if you wish, because we couldn't really model these systems more autonomously. I mean, we basically had to do it ourselves. We had to understand the system, and that was it, right? And then we did the categorization. So fast forward a little bit, a few years later, I think we have been, quite interested in actually then in sort of more formalizing this numerically, and this is what the talk will be about today. And we've thought more deeply, what is science? And I think one of the very compact way of actually understanding science is it's the art of differentiation. I think that's a very literal pun. Kind of PDEs, differential equations, are elementary to this, of course, but they're just one example, I think, of understanding, where shared things, shared operators, and where the things, where are components of the system that are going to be distinct, right, between different systems. Okay, and there's, another really important dimension here. When you're discovery, when you actually conducting discovery, you in this differentiation process, a system that conducts this process has to have some outside perspective. Okay, and if a system is closed, like Gödel showed in math, it excludes self-understanding. Right? So you have to have a perspective that is self-referential or referential from an outside perspective to really understand the limits of where your understanding ends. And you can see this in language models perfectly. A language model will not understand, of course, where its understanding ends. And people have thought about this a lot, and they are very frustrated by it, of course. And an LLM cannot understand what it doesn't know because it's trained to know. That's the probabilistic description. It's trained to predict what it knows, and it cannot understand what it doesn't know. It's not trained on this. Right? So this has to be done through a system perspective, I think, and we have to move away from, let's say, conventional, say, data-driven models or even PDEs. A model like a PDE, I want to kind of extend this idea. A differential equation is also not self-referential. It doesn't understand what it doesn't know. Okay, the PDE is, or a finite element model, is also a prediction that cannot by itself understand what it doesn't know. It requires you as a human to go in and say, well, this solution is not, accurate, or it doesn't satisfy the physics, or doesn't apply here. But it takes an outside agent to do that. And so this is no sort of the extension of this in AI, machine learning, whatever model we're building. We're going to have to build systems like this. And so what you see on the right is more of the kind of approach we've been taking in the last few years, is to build agentic systems that are able to, ideate something, reason over it, and falsify and verify, sort of have an outside perspective on how the world looks like. And then they have to be able to um, rewire the world. They have to be able to understand, things that were understand about themselves, what was wrong, what was correct, and update their beliefs about the world or their knowledge about the world. And And you can see sort of the fundamental problem here is, when you have, say, yeah, frozen weights, or if you have an LLM or one agent, it's unable to do this because it can't just update a belief. It has to, you either have to retrain the model or you have to find some other way of adapting the model. And people are working on this. And I think that's a very, very important direction, right? Because the idea, the concept of training a model and then letting the model sort of make predictions for science, for discovery, I think, is flawed, I think. And um, we have to find ways of creating models that can adapt, learn. That's the point of science, as I mentioned in the introduction. So this is a long introduction, but I think it's important, I think, for the debate right now on what does it mean to do AI for science. It means that we have to build models that can be wrong, and they have to understand that they were wrong, and they have to then be able to fix what they thought was wrong or include new truths about the world and so forth. So, we looked at this actually quite a bit, and when like with many things, many good ideas are not new, right? I mean, they actually have been brought up. Even AI has been brought up like in the 1700s in a way, as I showed earlier. But there are obviously, and even in sort of more you know, um, these agentic systems that I'll show a lot about today. They have been around for quite a while. In fact, in the 1970s, this is how we as a community started building AI at the time. There's air quotes here, but this was what the original idea was, right? Is building expert systems ultimately, and then they were programmed essentially to give you answers. And it's fascinating. And I watched I think a documentary about this actually from the 1980s when this was discussed as a novelty for novel industry system, that people were starting to use. It's fascinating how it was introduced. Of course, it didn't work because it didn't. First of all, it needed us humans, to program the machine. It couldn't update its own sort of understanding. It also was very brittle because unless the input and output was perfect, right, it didn't work anymore. And I think what happened, of course, now in the last few years, we've gotten some really interesting neural networks. So we have LLMs, which are, great in providing a glue. They're amazing program writers. They can write a program, a code, right, to run a simulation or to, from basic principles, solve a quantum mechanics equation or retrieve data, program a robot, right? So they have agency about, over code, over hardware, and they can collect new data. And they provide sort of a really good glue. So neural networks to me are amazing glues, between more symbolic representations, which are important for us to understand the world. So neurosymbolic methods, I think, are really powerful. And this is generally the framework that we're proposing and we've been working on the last couple of years here. And there are other, arguments we can make, about why can we build systems like this? Obviously, once you begin to think about the world of agents and function, there's this thesis that we have in materials that is pretty bold, I think, and it says, and so we start talking about this for a long time now, that you can achieve any function in a material if you have sufficient complexity in architecture. So there are some limits to this, if you need to have a certain strength and maybe there's a certain physical reality that's the limit. But in general, there's a very broad envelope of properties you can achieve. And we demonstrated this in the earlier papers actually on silk, hydrogen bonds, proteins, structure, showing essentially that if you have a sufficiently complex organization like here, right, you can create architectural complexity and you can achieve very, very diverse functions, even though you have the same building block, and this is what we call the UDP. And you also can see that if you add a control network to this, you can actually you're not stuck with the structure. In fact, you can update the structure as you solve the problem, essentially, right? So for material, this would be material solving a problem means it has to provide a strength. And what happens if the material starts to break at a certain part of the spider web, or maybe in an airplane, there's a crack forming, right? So how does the material respond to this? Now, in an airplane, there's no response. The material is really not intelligent. In a biological system, it's actually getting to the point where it's intelligence. There's a material intelligence built in. The spider can repair the web, Our blood vessels can repair themselves, our skin can repair itself, and this happens through these mechanisms. Okay, and so we've spent a lot of time actually studying these. We've studied them for blood vessels. This is an early paper from back in 2009. We've done studies like this for bone and many other systems. So there's a big literature out there from us and many other labs, of course, have worked on this. But the concept is always that we're going to expand this sort of space of hierarchical structure, property, process, and we're adding some regulatory network around it. And we want to model this, of course. And I think now that you were building models of intelligence, not materials. And the intelligence models materials, we follow a similar approach. And I think, compositionality is critical here because we're saying, well, if you can break down an outcome into compositional steps, you can trace them, like I said earlier. And you can model creativity in this way because ultimately creativity is the sort of combination of new ideas. Some of them are already connected, some of them are not yet connected. And the mental model that you build when you create something new as an engineer or designer is you ask a question, or as a scientist, you say, what if this were to be true? Okay. And so you're building a model where maybe some of those connections are not yet there, and you're asking, can they be there? Physically, is it possible to build a system like this with tools we have and so forth? And this type of thinking, I think, is critical to obviously to teach machines to be creative and solve problems. And that's one angle. The other one is, of course, now they have these baseline intelligence, which is pretty cool. I mean, we have, this is from actually a little bit last year, right? Okay, so now we have many better models and many more probably. But the idea was, okay, we have this exponential growth of capabilities, mainly in retrieval, I would argue, but some math, capabilities, especially if you use agents. And in science, the same thing. We can build scientific systems that have agents of these models. And so, yeah, the right-hand side sort of shows this picture of just a bunch of these agents working together. And there's practical things we're exploring, like how do you build a system that can solve a problem? What happens if you scale it? Like here, and I'll show this sort of towards the end of the talk. What if you take hundreds of these agents and you let them design a protein? And what if these agents have the same initial property? They're not predetermined in their functions, they're not fine-tuned, they're all the same. I mean, in a simple way, they're all ChatGPTs, but there are hundreds of them. They talk to each other and they learn from each other and they adapt how they behave. So can we do that? So I think ultimately this becomes interesting. Theoretically, there's obviously much more to say. I think these problems are ultimately, I think virtually all of them become reinforcement learning problems where we want to teach the model, give them incentive to solve a certain problem, and we're giving them a reward when they hit the jackpot, basically, right? And so the question is, what is that reward and how do we compute that? And I think one thing in science, so I mentioned earlier, we said science is the art of differentiation. This is a great, I think, objective or loss function, a reward function we can use because we can say if you can find a theory that explains everything, you win the jackpot. Okay. Now you expand your hypothesis further, and suddenly your theory breaks down somewhere. Okay. And now you have to find a better model. You have to expand how you think about the world. You have to think more, you have to think differently. You have to think more deeply about how you're going to build this model. And you're forced to do this. And so you're ultimately, step by step, you're creating more foundational theories, more unifying theories. Some theories are going to be different for different things. Okay, we penalize this because we want to have the unifying model, right? But the least reward is what the model gets for unexplained data. So if you have not no idea at all why certain things behave, then you are penalized for this. And so this is the reward function that we're using for the agentic model. So that's perhaps the most important insight I think we've learned from creating these systems. Now there's a lot of other stuff. There's how do we build it, how do we engineer these systems, but I think fundamentally thinking about the reward and how we bring this into a context, I think is really, really critical. And of course, we do not know the answer. So this is why I think, back to this, because we do not know the answer, obviously, in science. We have no training data. So all we have is this objective, that we want to create a general solution to a problem, and we do not know what the problem is because we have to create the problem, so we have to create hypotheses, and we have to close the system. And whenever we fail to close it, we have to expand our ability to think more deeply. And so this is what the machine will do. And there's, things I think we have to keep in mind. I mean, this talk is mainly on the theory and the simulation, but there are many other components. Obviously, there's characterization, there's the creation of the material or the system. And some of these things we do with collaborators, some we do in our own lab, as I've shown earlier. But um, it's a mix of many different techniques, and it is really an effort across many different scales, domains, people, labs, industries. Yeah, so it's a team effort in many ways. And yeah, so this is what we're going to talk about, and I'll give you examples. Everyone's probably wondering, where are the examples, and so I'll get to the some results as well, of course. But this is sort of in a nutshell, right? So we have different systems. We want to share abstractions, and we want to push the system to go outside of the training distribution and go discover new things, new materials, new designs, or new theories, right? Whatever we're looking for. And the system cannot be trained on this. Right? So when you train a model, you get this, we call it the Gödelian boundary, right? You get the limit, and the system cannot look outside of it. It has no understanding what's outside of that. So the way we can solve it, there's a couple of different ways to do it, but one way is to create agentic systems, right? To create different perspectives. And I think in human societies, this is how we do it. In our mind, we do it like this as well. We have a way of compartmentalizing how we think about something in different ways. And a good thinker will do that. We have to go do thought experiments. So this is critical to building the machine that can do this. Yeah, so we're using a sort of a bio-inspired method to this. And I think the early thing is, so we want to say a couple of points to make here. There are amazing things we can do in building really, targeted models. And every day you can read about better models for proteins, better models for, DNA, for this molecule, for chemistry. And I think what I'm really interested in is to say, well, first of all, what happens when you combine all these amazing models, right? You have sort of intelligence at a certain level about very, very specific tasks, like predicting the stability of collagen, or maybe unfolding proteins. This is just some examples from my lab that we worked on. These are amazing, but what if you wanted to say, well, I want to combine, okay, proteins, dynamics of protein prediction, materials design. This is a diffusion model to predict microstructures. What do we want to combine these? And so the early work we've done on this kind of idea was to build, this, we called it XLORA at the time, was a paper that introduced essentially different agents, but the agents were in the same model, if you wish. And the way we activated different agents and we made them talk to each other was through silent tokens. So this was sort of I think it's actually a very early example of what we now call a reasoning model. Right? So you know that in reasoning models we have reasoning tokens. Here we had every token we produced a silent token that was a token that essentially decided how the model should reconfigure itself. And that was the training objective. So we didn't train the model in the final stages of training to learn new things or learn new weights. We trained the model to figure out how to reconfigure the existing components, which we trained previously. So these are all the different expert models we had before. So this is, I think, and it's still an interesting strategy, I think, actually, to do this. And we saw that if you do inference with these models, they are very good. They actually do what we thought they might do, and you can visualize it here. You can see how the different layers in this architecture combine different skills essentially at different layers. So it's not just one expert chosen, another one. It's sort of the thinking process involves a lot of different experts. Right? So this is sort of a fast motion of producing an output. Like here, this is an output from protein design. We showed that you can retain a lot of the capabilities of the individual model. So this is one thing where we might not lose capabilities, right? Because we retain these capabilities, even though we can update the model's understanding of the world pretty well. And then, you have to create inference techniques as well, of course. So if you're interested, there's some work we've done in doing inference in Rust and creating these sort of inference engines, which is really important for these more complex architectures. So, sort of fast forward a little bit. I think I want to make sure move on. But we got really interested in graph models back in the day when we worked with category theory. Graph category theory is the ultimate, I think, graph model because it thinks about relationships. And I think that, for many of us in the field of machine learning, we're drawn early on as well to things like graph neural networks because they, naturally capture, let's say, the structure of a molecule, if you wish, right? Or maybe a spider web and so forth. And when we got interest, when a few years ago we had developed understanding that okay, we have maybe an ability now to not only predict compute on the graph, we can also form the graph through an operation. And then compute on the graph, we can combine sort of the best of both worlds. We can predict the graph from the data, depending on every context we provide. And we then compute on the graph. And this is the transformer architecture, of course. So this is why I think we've gotten pretty long runway with transformers because they're able to do that exactly. So this is in fact there's variations of the transformer we can build that are more expressive. Like in this paper, we actually produced a GIN transformer, which is a more expressive isomorphic graph model. But in general, every transformer is, of course, a graph neural network. So it produces a graph, and then it computes on the graph. And this is quite powerful, and we can even use these sort of general abilities to produce analytical representation of this. And so this is some work we've done later on. We made graphs explicit, analytical, and built kind of knowledge webs, if you wish, of data that we can produce from papers, literature, or even simulations that generate on the fly. And this, is very interesting because now when you're organizing the world into relationships, um, we saw at that point that we can actually try to do and maybe conduct these experiments that we've done previously in category theory. But now I can use a machine to do this. And so previously I created these maps by myself and I had to map the relationships to each other. But when I have a machine that can make this, and I can use an LLM to make this basically, or maybe a special purpose LLM if you want, but it can do this very well. You can compute on this and you can do things with this graph now that is entirely based on analytical symbolic operations. Okay. And this sort of was the foundation to a lot of effort then we started. So we started building agentic systems that had, included some of those graph structures as a way of creating hypotheses. This early model called Psi-agents. In this paper, we demonstrated, this is actually back in 2023, it's like an eternity ago, but in that paper, we showed for the first time that if I take a bunch of LLMs, in this case it was GPT-4, right? Do you remember the GPT-4? It was the first model actually that was able to write reasonable code and execute it through some sort of execution agent and do a bunch of other things. And so what we showed in this paper is that if you ask such an agentic system a question like, give me an energy landscape, it wouldn't just hallucinate the answer. Like if you were to ask machine learning potential, give me the energy landscape for this new configuration, you will never know if the answer is correct or not, right? And the same is true for any other model, by the way. I mean, even a conventional force field, of course, it'll give you an answer, but it might be wrong. And so what these systems allowed us to do is to say, well, the model actually could create its own data. It wasn't just relying on what it remembered, but it could actually write a program to run a code to collect, in this case, DFT data, and then use that data in producing an energy landscape, and then do a simulation with it. So this was, I think, for me, is a very exciting moment actually, and we've done, as you know, a ton of work in this sort of in this vein. I mean, we built agentic systems that solve real real problems. What I mean by that is not just creating an energy landscape, but actually designing proteins, solving continuum mechanics problems. Training its own AI models or machine learning models, circuits. I mean, there's many different things you can do. And still, we're still working on this. I think in the field, I think has really taken this up significantly. There's a lot of effort, big programs, a lot of labs getting into this. And the beauty of this, there are many, beautiful things about it, but one is that it liberates you in a way, right? You no longer have to decide, oh, I'm going to use physics or a pin or an LLM. Well, you can use all of these things together, right? So the tools, the agents, in fact, the ability of agents to make new tools on the fly, like write a new program and execute it, download a GitHub repository and creating a new, MCP server, maybe even on the fly, is real. So this fundamentally changes, I think, the agency that these models have, and with this, in fact, actually, we can really begin to see predictions that are out of distribution. So this is, I think, one of the answers to the problem that we saw in sort of single black box models I showed earlier that have no self-awareness. So these systems are beginning to create some sort of self-awareness as a society of models, if you wish, right? So this is still early, I think early days, but we're getting, I think, some very interesting results. You can see what these models do. So they write programs, they can correct the programs. I mean, you know, um, writing code, right, and executing code or writing a math lean program is, I think the lowest hanging fruit because you can run it, you get an answer, you get a signal. Science is a lot more difficult a lot of times because you don't know the answer and it's hard to prove. But if you can write a code, at a minimum, you can make sure it runs. And then if you have some way of checking whether the code is closed physically or physics is closed or, you can do that, right? So you can make sure the agents negotiate that solution and they can produce this on the fly. And of course, we're thinking about building this out into hardware as well. So we're thinking quite a lot about how do we connect these agents to not only simulations, which they can do, it can run simulations, collect data. How do we connect it to, let's say, a 3D printer? How do we collect output from the 3D printing process? Last year, 2025, we published this open source manufacturing system, which is a very simple, I think, good system actually. So check it out. It's on GitHub. It's totally open source. You can build it yourself, basically, if you want. The entire part list is there. You can make it. And it's made essentially to have a very interactive way of, telling the printer to create something and then collecting data back. So that's the vision for this system. And we built this in our lab. So this the student Jesse called it Beaver. So that's the system you can find on GitHub. So there is, with this, I'm going to show, there is agency not only with software, with codes, with tools, right? So you can have physics simulators, AI models, all these special purpose models I showed earlier, they just become tools in the system. So I think the world looks very different now, right? Because it's not you deciding necessarily which tool to use, but you just tell the agents, the planning agent, what are the tools you have, make a plan, and then see what happens, and then go back. And when I say see what happens, this is the hard part. But the I talked a little bit earlier about the objective, right? So if you're deciding on a design problem, the what happens means is your design good enough to meet the target, right? So it's easy, okay? And then you go through multiple iterations and you produce outcomes that work. If you're doing science, the objective or the reward function has to be a little bit different. And I mentioned earlier how we think about the problem to have generalizability as a reward. And the agents actually will run in circles, like in real science, right? In human-driven science, they will continually try to break the world model, and they will continually update the world model to become better. And so, kind of looking at the spectrum here, you basically organize all the knowledge and you hypothesize new ideas, new connections. Some of these connections, you could prove them out, great. You adapt them to your representation of what you know to be true. Others are not, and you can erase them. So this symbolic representation is absolutely critical for letting the agents learn and adapt and change their behavior. And there's papers on this if you're interested in seeing how we're constructing some of those graphs. There's a bunch of papers we've published over the years. Um, and I want to say to these graphs, I think they're very interesting, obviously, for many reasons, especially mathematically. I think, when you organize thoughts as a graph, which is basically a relational model, which is essentially what category theory teaches us or demands of us to do, we have a very efficient representation. In fact, empirically, we can show this. And these are all small world scale-free networks. So they compress information effectively. And it also means that if you're going out, the other direction, if you want to hypothesize something new, you can do this with an ex combinatorial explosion. I can ask the question, what are the different ways of connecting point A to point B? There's a lot of different ways. And all of these ways are hypotheses. And you can ask questions about things you already have, like connecting concepts, or you can ask questions about, what if a connection would exist? What would that unlock? Okay, and this is the kind of thing that we can use actually in making the machine think like a scientist, like an engineer, and really understand the world as opposed to just approximating the world. So this is what we call a neurosymbolic approach, which is the core of a lot of the stuff we do. And you can see this here, very, very rich representation, of course, of the world. And using this in the agent systems allows us to solve problems and create very creative solutions. That's still the key here. So we're really going outside of distribution because, of course, the training of a language model or of an agent or maybe even a chroma model or AlphaFold model it's just based on existing proteins. So it just basically trains what we have. But using an external neurosymbolic method allows us to hypothesize very new ways of designing a protein. The agents can then validate this. So this is the key. Now that we have a physics engine, we have maybe a protein surrogate model that we can even update, we can retrain it or update or fine tune it. We can build a better and better model of the world, and it can change as the agents think through a problem. So this is what I mentioned at the very beginning, right? So we're moving away from, I think, saying, oh, we need all this data, we're going to train this big model, and we get answers, to say, yeah, we need, of course, some baseline intelligence. We have it, actually, and a lot of times we have these models now. And we then got to figure out what is the machine sort of that works at the meta layer beyond the individual model. Okay. And so I'll skip through some of these things because I know we're almost out of time. So there are many applications we've used this for. We have done work on proteins, on continuum mechanics, so early example. We've also applied this to discovery. So this is what I mentioned earlier. This function here is essentially our reward expression that tries to capture mathematically that a model, an understanding of a particular system has to cover as much as possible with a unifying theory. It has to be, it will be penalized if it cannot organize the world. And so this is what the last term is. So this is a penalty if the model just has sort of throws his hand up and says, I don't understand how to explain this. And if the model has intermediate representations or partial representations, we allow that, but we penalize it. And so the thing that we really want, of course, is that everything falls under a unified representation of the world. And so this is, I think, how these agents are incentivized to do work. And they work sort of through this process. They ideate, they reflect, they experiment. And what this experimentation means in the Sparks model, originally we don't have any hardware connection. We just use in silico, so we might make a plan. We either call a function or write a program to run a physics simulator. We get data, we reason, we reflect. Okay, and if we're done, we're writing the final report, but usually we go multiple iterations and we create a new hypothesis. We ideate again, go back and kind of repeat this process multiple times. And so what comes out of this? So if you're interested, this is it's in submission, but it's also on arXiv. You can find it there. These are essentially so nowadays they're called AI scientists. Basically, there's a whole class now of models out there, but this was I think one of the first models like this actually produced. And what this model can do is it can do science, and what it means is it can take a very general question and it explores, it produces data on its own. So it's not just reading papers and making a summary. It actually hypothesizes something that is either wrong or true, but there's a spectrum of what the outcome will be. We write a executable program that either runs code or runs an experiment, and it collects data and then produces an insight, that either it falsifies or verifies the model of the world. And if it's true, okay, then the agents will be challenged to create an even more complex problem or hypothesis. So we're always expanding beyond the limit of good, basically, right? We're always expanding beyond, beyond, beyond. And the job of the agents is to figure out how we build a better model. And ultimately, once we've spent enough compute, we're out of tokens, I guess, or out of compute time. We have to write a report at some point and write a report. And the all these reports, there's a couple of examples in the paper, are entirely AI generated. So this I think the first time, if I would have seen this paper um, 10 years ago, 5 years ago, maybe 2 years ago, and you would have put a name on it, right? And a human name, I would have not questioned that. I was, yeah, I mean, of course, a human made this. So the machine is so good, I think that it passes the Turing test, the science Turing test, if you wish. And there's still work to do. So this is the frontier, and this works well for certain areas like proteins, where we have a lot of biological tools and data methods, but it doesn't work everywhere, of course, but it is very, very exciting. So we've done this for proteins, we've done it for this is Box Matter. So we actually connected the MatterGen model and the materials project. So this is an example where you can basically just with a few lines of code, you can change this model and say, hey, I want you to use a generative model for materials, for inorganic materials, and I want you to, by the way, also have access to big database, and then you can solve other kinds of problems, and you can obviously be much better. And this is what this table shows. It's all in the paper. We can be much better than any frontier LLM or any frontier surrogate model on its own, right? Because we validate predictions and we have a very deep understanding. So there's a bunch of designs we've made using this model. So it sort of challenges a little bit the early Gen AI, as you know, they produced really cool ideas, but a lot of times people found out when they dig a little bit deeper into the ideas that the models produced, it wasn't stable, or the model wasn't actually, it was already known. And so what we're doing with the agents here is essentially put another meta layer around it where the model has to think through these questions, okay, and actually come up with something that's actually new and actually stable and so forth. So these agentic systems are very, very good for this. So they can produce many different solutions, which are, I would argue, more physically admissible and viable than previous examples. Now, the last thing I want to show maybe is actually two things I want to show. Is I don't know, Vivek, how much time do I have? Do I have a few minutes or um
It's all right. I think you can go ahead. It's very
okay, I'll just
interesting, so
spend
please complete it. Yeah.
all right, thank you. Yeah. So I'll spend, I mean, I'll jump through a couple of things, but first thing I want to show are graph native reasoning models. And so this is a big topic by itself. So it could be a whole talk by itself, how we build these, but these are models that are reasoning models. They have sort of silent tokens, but not just one per token, but they have sort of more traditional reasoning structures, thinking tokens, and they produce in the thinking process graphs. So this is the direction we're very interested in, and I hope some of you will become also very interested in this because I think that's an important direction actually to explore. And why is this? Because first of all, if you have a symbolic representation of your thinking process, all of these, category theory ideas and the compositionality that I talked about earlier that we can produce or think about are now created during the reasoning process. So when you make a model think in graphs, you have a verifiability. You can test every single compositional reasoning step, right? So a traditional reasoning model will produce pages and pages of text, sometimes 8,000, 20,000 tokens, and you can't really verify everything. I mean, you can read it and check it out and maybe, but there's no step-by-step proof that things actually are true. But of course, you can see this here. This is the actual reasoning output. So if you think in graphs and relationships, you can prove out everything. You can actually fix, incorrect steps in the reasoning process. And so there's a very, very, strong, traceability, compositionality in there. And also it's very efficient because, of course, as we mentioned earlier, we can exploit small world properties, very, very efficiently. So if you think in graphs, things are great, they're efficient. You can let this process run for a long time. So we did an experiment where we took this graph native reasoning system and let it sort of, build a graph every time, right? And then we let it ask another question based on the previous outcome. And we wanted to see, what is the model going to do? I mean, is it just going to drift off and produce sort of disconnected concepts, or is there something more? And what came out of this actually is that if you let the model think longer, you basically you don't let the model stop thinking, you let it continue to think, it will produce increasingly complex representations or graphs, which never saturate. We ran this for thousands of iterations, and the graph keeps growing, and there's significant diversity in there. So there's no collapse essentially, or no dissociation. So there's a really well-connected structure. And so this is sort of an example, I think, how if you want to think about building, test time compute or reasoning models that are, traceable, compositional, but also can be richer as they think for longer. This is a proof that they actually do this. Right? So there's mathematically you can show. There's a bunch of different analyses we've done where we published this. So this is in a paper in Chaos, actually, where we looked at this, the dynamics of this process in a little more detail and computed structural and semantic entropy, which is a measure to sort of to look at the structure and the semantic organization of these graphs, how they evolve over time. There's some, I think, really interesting behaviors. Here, so we treated the system basically as an experimental setup. We let it think and we studied what comes out of this process. And I think there's really interesting insights from this. So this is one area I think I want to, if you're interested in reasoning models, check those out. There's a bunch of papers on graph native reasoning models from my group. We even have recipes online on our GitHub how to make them. So if you want to check them out, so go to LAM MIT and you'll find a bunch of different recipes there to train your own models like this. The last thing I want to show are these swarm intelligence systems. So this is more recent work where we said, okay, what if you, so one thing, of course, that if you were in the AI field, what bothers you probably if you see agents, you say, well, we're humanizing these agents. We're putting a lot of human intuition. So sort of the same mistake, if you wish, that Myson made back in the day, where they created these expert systems and they said, we're going to program them. We decide we need a planning agent, we need a coding agent, we need a protein agent, right? And so actually, from an engineering perspective, that's totally fine because you can engineer really cool technologies with this. But what if you didn't want to do that? What if you wanted to sort of have just general agents? They're born the same way, just like ants are born the same way. And you make these agents learn as they solve a problem. So they're all the same, no specialization at all. And can they learn and actually organize themselves? This is sort of what you see here, is the organization of the system as the problem is solved. And is this stable? I mean, if you take a bunch of agents and you let them learn, basically adapt how they behave, they learn from a reward they're getting. What are they going to do? Are they going to become, are they go crazy, basically? Do they have no organization? Do they have organization? Can they solve a problem? Do they stabilize? And the answer is actually yes, they stabilize. So in fact, they form a sort of a society or civilization, if you wish, or group of traits that are different. They do not remain the same. They become different, and they collaborate and they can solve problems. And it's the interesting thing. This is really great work that my student Fiona Wang did. I don't think she's actually in this seminar right now, but she built the system. Basically, we started by creating. We used couple of dozens or hundreds of agents, off-the-shelf LLMs in this case, and we said, can these agents actually design proteins, first of all, right? And can they do it better than a conventional model? I mean, can they go outside the training distribution? And the answer was yes, actually. So, and here's a picture of kind of the data. So if you look at all natural proteins, it meets sort of it matches a very, very small space in a huge complexity of what's possible. And so you can basically make many, many more proteins that are useful probably than nature has ever tried. And that's the space we want to get into, right? So we don't want to stay around sort of the planet Earth with the proteins. We want to go really out here. And so yeah, difficult, these conventional models cannot do this because they're trained on all the natural proteins. It's like the fire example at the beginning, they're trained on how to make fire. But if I want to really advance science, I don't want to create another way to make fire. I mean, it's useful sometimes if I'm an engineer and I want to adapt something, right? But a lot of times I want to change the equation literally. I want to discover something fundamentally new. So we have to have compositionality in this case. And so we are applying these, by the way, to all these different use cases, from food to fibers, plastic replacements, and so forth. So in a nutshell, so we took these agents, we took off-the-shelf LLMs, put them in a big group, and they're all the same, N copies, right? And they have no training whatsoever on proteins, by the way. I mean, they have some understanding of proteins, like ChatGPT has, but nothing more than that. And the experiment was if they can talk to each other. They have episodic memories, or they deposit what they do. They have their own history of actions and what the outcome was on the global objective. They can see that. And their job essentially is to figure out how to adapt their behavior, how to change themselves to better achieve the outcome. So it is totally fascinating, I think, because self-organization, but with intelligence, and is a very different approach, obviously, than the traditional way of doing things, where you would have pre-training, fine-tuning, deploy a model, kind of the same way. And it works really well. So these models actually, can solve extremely complex problems. They can solve protein design problems. They give you, I mean, of course, we can run this many times and we can understand the distribution of solutions. And what's really cool about this is, you can see what kind of solutions they come up with. I mean, are they random? No, they're actually not. They follow design principles. And some of those insights you see here are actually by themselves scientific insights, because these are the design principles that make certain things happen in biology and proteins. And these are, if you compare the performance, here's another objective on dynamics. So actually, we took the VibeGen model we've trained recently, the diffusion model for dynamics of proteins, and we asked, can our swarm do the same thing without being trained on all the data? The answer was yes. It's kind of, I wouldn't say it's depressing, but it's sort of a sign of the time. I mean, we showed basically that if you don't need the special model anymore. I just need a swarm of agents and an objective, and they can produce the outcome just like before, but I don't need to train the model. So there's a bunch of examples in the paper. You can take a look. We also studied a little bit in the paper how this happens, sort of how do these swarms solve the problem? So like kind of like the chaos paper I showed earlier, where we looked a little bit into the dynamics. There's a very rich set of information, obviously. We haven't mined all of it. I mean, there's many, many other things one can study, but that is another really cool area, I think, to go in and study how swarms actually behave. And I mentioned control theory earlier. So the idea that, okay, if I have maybe a better feedback mechanism, a better control theory, or I can learn a control theory, there's a lot of really, really interesting things. This is something I'm starting to work on with some colleagues at Carnegie Mellon, actually, to think about these mechanisms, Larry Buehler. And so, yeah, so there are, many different things to say about this, but one maybe the most important thing is, so how do these things look like? I mean, and one sort of outcome was that, yes, these predictions are way out of distribution. They're far away from natural proteins, which is great. You can plot these clades, sort of the difference to the distance basically to known sequences. So the center here is the universe of all the known proteins. And then you can see we really go outside of that really, really far. And we benchmarked this against state-of-the-art protein models. And we could show that, yes, we can create more diverse solutions, and better solutions, obviously, um, without any particular fine-tuning. So we really have, I think, something at our fingertips here I think it's exciting to explore. Right? More work needed, but this is really recent work. It's still in review, but it's all in archive, so you can check it out, and a little more analysis here. And the same thing, by the way, what's really interesting about this is that the same technology, the same algorithm, exact same algorithm works also for totally different things, because it's a swarm. So if you tell a swarm, make a protein, or now I'm telling a swarm, create music, it works the same way. So I have quite a lot of background in music composition, and in both scholarly work and also work with artists and orchestras. So just to give you that credentials, I'm not just walking into this as a complete newbie. So I have a lot of background in music theory and composition itself. So I've written, pieces for orchestra myself manually. So not AI. This is me doing it. Okay, but and so we're working this for a long time. So the question here was, can a swarm of these agents actually write music and do it in a creative way, in an intelligent way that would impress me as a human? And give you sort of the story here. So this, I'll skip over this. Um, it works. Okay, so the same architecture, same algorithm, and the swarm actually is much better than a conventional music generation model. And so to explain this, now here we're not dealing with science, right? We're dealing with something. How do you measure this, right? So you can measure in different ways. You can measure the quality of something that you created by creativity. How do you measure creativity? Well, you can look at things like the different building blocks we've used, right? So for example, the swarm uses many more different note durations than the traditional, single shot composition process. And now, if you listen to the music, though, and we're not going to do this here, but you can find it as part of the paper. Um, the single shot bass line sounds really good, but when you listen to it a second time, it sounds really boring. It's like a pop song. It's basically using the existing paradigm of writing music. The Swarm created music that when I listened to it the first time, actually, I thought it was total nonsense. And I made many different pieces, many different compositions. And I realized actually after a while that I really had to learn what the Swarm literally was trying to tell me. It took me effort, intellectual effort to understand the music. And I realized after a while this was actually precisely the act of good creativity, is something that as a human you don't get it right away. You have to think through and then you understand it. So the machine is telling me something here that I did not understand at first sight. And I think this is a sign of creativity. I think is something here that is different than if you just let a machine create something. Like if you use Suno, it's amazing, but it creates music that you will probably like. Every time you run Suno, it will create music that sounds pretty good, right? But Suno is not going to create a new form of a symphony, right? And here, the swarms, I think, is one such way where you can actually really go out of distribution. So this is the equivalent, essentially, to doing science in the creative space. And we can quantify this too. I think, obviously, in the more math we can apply, the better. We gave each agent a trait vector, and we measured this, and we basically said, as these agents work on the music, and they go through iterations step by step by step, they're going to adapt themselves. Are they going to converge, right? And they do. So there's no divergence. There's no, a drift going on where they just become sort of random acting kind of systems. They converge as the score maximizes, which is the outcome, the quality of the music. And happy to talk about how we measure that later if you want. But we can make this, obviously into actual audio. So we compose this symbolically using score, and then we made it into audio, analyze the audio, and I will skip this because I think Vivek's pointing that we have to end. But there is math you can do on the graph, obviously, and we can actually analyze the graph structure and got some really interesting insights from the actual audio structure, which we measure using self-similarity. That's a common way to analyze structure in sort of in domains like this. So let me go to the end. So I'll leave you with this final example here, final slide. So the sort of the beginning was to talk about AI machine learning, right? So we tell models what we know, teach them on all the knowledge in the world. This is the machine we're interested in building, where we the machine itself shapes the world. It creates new insights, it creates new understanding of the world, and because it has agency, ideally, in actually building these materials, either it tells the human to do it or it tells a robot to do it, it changes the world. So this is, I think, where we are actually. We're beginning to build these machines. So that's our passion, and my lab is dedicated to achieving this with the community. And happy to talk more about this. Thank you so much.
Thank you, Professor Buehler, for the amazing talk. It was very interesting and kind of groundbreaking. Thank you for taking your time to present your work. So for the sake of time, maybe we could take two quick questions for Professor Buehler.
Hi, I have a question. My name is Aditi, and I'm a third year PhD student working with Professor George.
Mm.
Um, Great talk. Uh, you mentioned about using isomorphism between two structures and then sort of like treating those two categories and making some sort of connection between them. My question is, how does it relate with physical, like to see that, okay, this thing is realizable physically? For
Right.
instance, if I have, say, a lot of swarms, I have swarms and I use um in some way I take map them as like a whole, a knowledge graph of things. I use Ramsey theory to say that, okay, there's an underlying substructure I have. I use category theory to say that I can map it to some other category and this is possible. It has mathematical underpinnings, but is it physically feasible? Like, I don't know about like whether that is true in category B or not. What I'm seeing
Yes,
in category A. Yeah.
exactly. Yeah, I mean, has a great point. I mean, there are many different ways by which we can mine the graph. One is
Uh-huh.
a transitive connection, one is the isomorphism. Okay, and I think so your question already is part of the answer. Let me explain what I mean by this. So a really difficult thing for an AI, actually, for an artificial intelligence system is to create a hypothesis. It's very hard because a hypothesis that the model might create is oftentimes a trivial hypothesis. And if you ask ChatGPT, make up, it's actually what's already known. It might be new to you, but it's not new to the field. And so by using the isomorphism, at a minimum, you're getting really great hypotheses because you can say, okay, I have a behavior structure here, I have a structure over here, I have an extension of the structure in my one domain. How could I extend it in the other domain? And you can create an actual hypothesis mathematically by using embeddings. So you can say, I'm putting all these nodes in an embedding dimension, and I'm basically solving the inverse problem of what node would it be if I'm following the same structure and movement in my embedding space. So it's like the early work on embedding models and movements in
Mhm.
embedding models. So this is one way to do it mathematically. You can also use language models actually quite effectively for this because they have, if you talk to them, basically you're decoding this information. You're not just working in embedding space, you're decoding the embedding space into tokens, and you can ask them questions like this. You can say, I have
Right.
this
Yeah.
graph. Yeah, so there's this practical way. This is how we've done it in most of the times. We've also used the embedding experiment, but very simple, it would be this. Yeah. So you're creating theses for what might be true.
Uh-huh.
Um, and then of course, you have to create closure based on physics.
Right.
Yeah.
So when you say isomorphism, do you use it in the sense of like I have two graphs, if I'm able to label them in some similar way, that's isomorphism. That's it. Or
Yeah.
like, does it satisfy the three isomorphism theorems?
Yeah, you basically map them. You have to be able to map them topologically to each
Okay,
other.
I see.
Um,
Okay.
and of course, in reality, it's always a subgraph. Right? So you find
Mhm.
the smallest or no, sorry, the biggest possible subgraph that still allows you to map them. And then you get sort of you can overlay them basically. Imagine and
Mhm.
you
Yeah,
have one
right.
graph
That's what I mean.
continues over here, the other one continues over here, and you can say, well, I have something here that maybe there's a connection here. Yeah.
Yeah.
The other things you can do, you can map the two graphs into a shared abstraction. Right, so this is the way I think we think about it typically. So you think about what are the different ways of creating robustness. And you find robustness in this system, in that system, this system, and the robustness actually is expressed as a symbolic graph, right? And so you have real symbolic operations, first order
Yeah.
logic or other things. So if you do this, I think you get you get an even richer or more pure mathematical description of this. So you have sort of two functors, one functor to the symbolic expression and then another one to the other one, and then you connect them this way. So there's another way of doing this. Yeah,
Thank you so much.
cool.
Thank you, Aditi. We have two questions in the chat. First one is from Nicholas E. Thank you so I'm reading it out loud. Thank you for your talk. You mentioned several times the notion of true discovery and intelligence. There is an ongoing debate about whether transform-based LLMs, even when scaled and tool-augmented, are sufficient for that, or whether fundamentally different underlying models such as JEPA or world model-based approaches are required. Where do you stand on this?
Yeah, well, yes, yeah, yes. I mean, I think You need a world, yeah, you need some world model of some sort. Is what I talked about. Right. You can't.
Right,
I think an LLM. So it's still a debate. I think LLM
right.
without a tool. I think that debate is over. I mean, some people don't believe it, but I think that's clear. I think just mathematically
Right,
you can prove an LLM with a tool. It can do things, but then if you have an LLM with a tool without a memory, without a world model, memory world model, okay, it also doesn't help you because the LLM is just doesn't remember anything. It just keeps going back to what it
right,
believed before. But if you have an
right,
LLM with a tool and with a memory layer, world model, JPA model is another way of writing it out, essentially, then things become interesting. So my thesis is exactly along the same direction. And I think there are different ways you can build these world models. JPA is one of them. There are neurosymbolic approaches, which is what we've been using. And there might be others. I think there's probably going to be a multitude of different solutions to this, but you need an externality. And I mean, in a nutshell, so you need to truly create. I wouldn't even say it's even with like a JEPA model itself. Probably you can't, predict out of distribution, but you need an externality. You need self-referentiality. You need to be able to reference yourself and understand your limitations. That is the key. So that's why I talked about Gödel a little bit. It's something that I think you have to understand. So if we have that, then various kinds of models, and you can develop this. Now, the question is what baseline intelligence you have. It's like having a bunch of snails talking to each other. They're not going to really figure things out. A bunch of ants can actually figure things out, and humans are more intelligent, but there's obviously much higher levels of intelligence we can build beyond ours. And I think
right.
the difference there is that they have a self-awareness at some point. How that
Yeah,
emerges is an open question, but I think, at least from
right,
our primitive understanding right now, we need an externality to the system.
right. Thank you. So we have one question from Professor Yanis Kavrikides. Thanks, Marcus. Somehow, successful collaboration implies that an agent forms a decent internal model of the agents it works with. Can you see this example in your agents form experiments?
Yes, I mean, and I know what you're asking. I mean, it's a very difficult question, but yeah, yes, I think that is true. One way we measured it is based on the traits of the agents. So that's sort of a proxy for what they've learned, how they behave. And it has to converge. They can't sort of randomly talk to each other and not learn anything useful. They have to come together. It's like it's an organization where there's a convergence of how they become and how they interact and what they've learned. And now I think the deeper question is if to measure this, I think what I like to do is I like to actually build the representation. Right now, the representations are either a graph or it's whatever the agents deposit. They might deposit an equation, like in the protein example, a scaling law. But I think we can formalize it more. And I think the answer to this is we're going to have to look at many experiments and we have to find a way of measuring it mathematically. Maybe one way would be to train a model, could be a neural network, could be some other surrogate model, um, and to see if there are structures that correlate between
Yeah. Well,
good solutions. Yeah.
I'd say with all your experience, it would be interesting to maybe think of an experiment in which that is the goal of your campaign, like try and have a system that will more shed light on this as opposed to solve science. It would be
Yeah,
an interesting.
exactly.
Thank you.
Yeah. No, absolutely. Yeah. And I think so the way I like to do this is I think one way is to deposit the world model as a graph structure. And the advantage there is that we can analyze it mathematically quite well. And we can see whether my hypothesis would be that if you have agents that have solved the problem effectively create a more efficient world model, a more general world model, meaning a graph of certain properties, as opposed to agents that don't do this. And I think we can then figure out this is essentially the collaboration mechanism that they use. Yeah, that's how they communicate.
Thank you. So the last and the final question, It's from Varun Kumar. How can we verify if the graphs generated using LLMs are valid?
So I'm going to answer provocatively. They're probably not valid. Okay, I'm joking, but no, so this is the most important question actually there are many important questions you guys all asked, but I didn't say this actually, and it's very important that everyone takes this away, so don't leave yet. No, the graph is not the truth. It might be, but it might be wrong. But the point of the graph, if you're thinking about the graph, right, it's a way of writing down what we believe to be true and then validating or falsifying it. So generally when we mine the data from papers and we make a graph, it's a substrate. Like we call it a reasoning substrate. It's something to think through, think about, think with, think against. And the agents, the physics, essentially are used to test out these ideas. I mean, the graph is used for hypothesis generation. We're just using the graph to generate ideas, right? And then we're doing science on them. We're executing physics. We're running simulations. We're testing out whether this is actually true. In the world model question that Yanis was just asking, the point of the graph is to deposit how we think the world behaves. But I mean, the graph might be a PDE, right? This is a very efficient way of describing the world. Is this what comes out of that, right? So the graph is really a memory layer, but it's a symbolic memory layer. And it's glued together by neural networks. That's the thesis we have, I think, today, at least what we have today. I mean, we have sort of found interesting combinations of tools that work well together. Yeah, neurosymbolic methods, I think, are very powerful. Does it answer the question?
Yeah, thank you. I actually worked with your code, and I found something very similar that some of the nodes in the graph are not very useful. So basically, you have to find a way to like filter them out in some way. But yeah, I think I agree with what you just said about the graph not being the end-all result.
Exactly. That's exactly the point. Yeah, I mean, it's exactly the point. So in fact, actually, this is what I think is a very important question or an answer, because when people tried using what they call knowledge graphs, these methods fail a lot of times because there's so much garbage in there. And I think what we changed here in our perspective is we don't call it, we might have called it knowledge graph in some papers, but we don't see it like it's not the truth. It's a possibility of what the truth might be. And it allows the machine to do things that we would usually do, like what are the possible connections? And is this connection true? I mean, it's sort of how we do things, but without telling the machine what to do, we can just let the machine compute on the graph. Right? So it's an extension of the transformer architecture. Actually, it is an extension of the transformer architecture, but it's externalized. So this is something in my head. I'm not exactly, I don't think we really understand yet where if the LLM scaling argument is true, actually, perhaps it's going to be around the question of, where does the LLM create a certain capability of dividing itself into multiple completely different perspectives in its thinking process, and it sort of overcomes the limits of Gödel, if you want to put it that way. I don't think it's possible, but if it is true, that scaling alone can do that. I mean, it would be some sort of metaphysical maybe occurrence where you have a separation, and I don't know. But yeah, so there's an externalization of the graph compute essentially that you create using this knowledge graph in quotation mark.
Thanks.
Thank you.
All right.
For all the
thank you so much.
Thank you, Professor Buehler. It was such a
Thank
great
you so
talk.
much.
Thank you for taking
And please, questions, reach out to me by email, visit me at MIT. Always happy to chat. This is very exciting. So thank you so much.
Thank you. Yingheng Tang is a postdoctoral researcher in the Center for Computational Sciences and Engineering at Lawrence Berkeley National Laboratory. He earned his PhD in Electrical and Computer Engineering from Purdue University. His current research focuses on developing AI foundation models for scientific discovery, with applications in microelectronics, photonics, and quantum systems. Additionally, he works on HPC-driven numerical modeling to study problems that span multiple physical and temporal scales. With this brief introduction, I invite Yingheng to present his work.
Okay, so can I start?
Yes, please.
Okay, yeah. Thank you for the introduction. So I'm Minghan, and I'm currently working in LBL, and I'm with essentially applied math department. So today I'm gonna present my work on our recent work regarding MatterChat, which is a multi-modal LLM for material science. So yeah, first, before I start, I want to do some background introduction regarding the motivation for our previous work. So and our group's work. So essentially, we are our group at LBL are working on microelectronics related modeling, and since the nowadays it's the Moore's law is coming to an end, so we are in the desperate need of new materials, and which brings up the need, a great need to do modeling at different scales. So like the modeling can span with from different scales all the way from the material, which is from the atomic level to the junction, the device level, and all the way up to the circuit level. So our team are essentially working on all kinds of all the pipelines. So as this figure shows, each scale has their own modeling theories and modeling tools. For example, for the material modeling, typically people using the density function theories, like there are tools like FAST, quantum espresso, for those problems. And for junction modelings, there are tools like LS3DF. And for devices, we have like electromagnetic modeling. I listed Artemis here as our designed HPC-driven EM modeling. And if we going up to upscales, we will be using, like people will be using Cadence and the tools like System Verilog to model a circuit and systems. So, however, these tools are not do not naturally communicate with each other, and many of them, their computing kernels can be very extremely expensive. So this kind of motivates us to combining HPC and machine learning to accelerate the simulation and try to connecting the information across different scales for accurate whole pipeline modeling. So this is the previous work from our team. So like we have done various work in different scales modelings. So from the atomic scale, we recently have the MatterChat, which is the topic that I'm going to present. And in terms of mesoscale level, we have like a hybrid model for magnetic device modeling. We also have like a wave foundation model, which we have one paper out, and we are in the process of developing one foundation model for general wave phenomena as well. And we also have several works on the system level, where we utilizing the whole pipeline modeling to model a analog neural network architecture. Yeah. So, but like for today, I'm mainly talking about the MatterChat. So this slide shows a general evolution of the modeling method that for material science. So as you can see from the top right figure, so starting from the 1970s, there are the traditional computing method like density function theory started to emerge, and those traditional methods are very accurate, but they are computationally very expensive. And when the time moves to around 2000 to 2010, then the ML approach starts to show up. And regarding the physics ML models, it starts from the conventional ML model, and then to the deep learning model, and then to the recent foundation model area. As you can see from the bottom left figure, the number of the foundation model, graphic-based foundation model in material science starts to like coming up in a very fast rate, like especially after 2020. So and the third approach is like the LLMs. So after 2020, especially probably 2022, when the GPT 3.5 shows up, like people are starting to using those to solve all kinds of like questions, and the general LLM, like the general purpose LLMs are evolving also very extremely fast, and has excelled in tasks like in many scientific and non-scientific domains. And this slide shows the but like for the physical ML model, the physical ML model is fast, but it's often bounded with single task, and many times there are lack of interpretation ability. And also what's important is also lacking the human AI interaction. And currently LLM, even though it's a very hot topic, and as I mentioned, many people are using LLMs to solve their problems, but in material science, typically when people using LLMs, a convention or a naive way is to using a pipeline approach, meaning you have a certain structure, either for inorganic materials is coming in a format of the crystalline graph.cif format, or a SMILE format for organic or molecular material. But like then the pipeline approach is you took those CIF files, and then you tokenize them as text, and then feed them into the LLM with your pipeline to get the output. I mean, this pipeline works, but it generally fails to leverage the coherent spatial relationship directly between atoms. So you will purely rely on the attention mechanism when you do the fine tune of the LLM. So that's the main motivation for us to try to think of a way that can effectively combine the two modalities, the graphic representation of the structure and the text together. Yeah. So then our goal is to building a multimodal LLM that can directly integrating these two together. Yeah. So this slide shows the core architecture of the MetaChat. So as I mentioned, the primary design goal here is to bring the two distinct modalities, and so here, instead of training a massive end-to-end model from scratch, which would be extremely computationally expensive, and here we choose a modular structure-aware frameworks. So notice the component marks in blue. So the physics model and the LLMs are all kept frozen. So the physics model are taken from the pre-trained foundation model GCNs, the encoder part of the foundation model GCNs. So here we use so here in this physical model we're currently using the one invariant version of the GCN, which is ChargeNet, and for the LLMs we're using an open source LLMs, which is a Mistral 7 billion. So by freezing those two ways, we can preserve the specialized the physical knowledge of the graphic encoder, and the general purpose logic of the Mistral LLM. So our task then becomes much simpler, which is to train a connected module, the bridge module. So if you look at the top range, so the material structure is first converted into the graph, and then will pass into the physics model, and the physics model will extract the raw atomic embeddings, and then the embeddings will be fed into the bridge model. So the bridge model here is a 3-layer transformer structure, but with various trainable queries. So when the atomic embedding passing into the bridge model, so you will perform self-attention at every odd layer, but it will perform cross-attention with the trainable queries at every even layer. So in that case, the trainable queries will further extract the useful information from the raw atomic embeddings. And after the 12 layers, after the final layer of the transformer, you are passing through a projection layer. which is to make sure that the output has it is dimensionally compatible with the language embedding, and the language which will, or the language or the user prompt which will come in as a format of the question will be passed through the pre-trained model, the tokenizer, and the embedding layer of the pre-trained LLMs. And then the language embeddings and the query embeddings will be combined together and feed into the LLM transformer structures, generating the system output. Yeah. So like to train, so here the model is highly modulated, so we only need to train a relatively lightweight bridge model. So the bridge model, the starting weight we are using is the BERT-based model, which is around 700,000 parameters. So overall, the model is trained on NERSC, NERSC supercomputer in LBL, and we are training the whole model using 32 A100 GPUs with data parallelization strategies. Yeah. So this slide shows illustrate the data set and the task distribution. So we are the training data that we are curating is from the open source data set, which is the material project, and the material project that we're using almost all of the structures from material project, which is around 140,000 different structures. And as you can see, the periodic table shows the distribution of the chemical compositions, chemical elements contains in those structures. As you can see, like it's the data set is very comprehensive, and it's essentially covered almost all of the chemical elements. And for the downstream tasks, so we currently have like 11 tasks. So 3 of them is descriptive tasks, including the chemical composition, prediction, and the space group and the crystal system. So the latter 2 are for the geometry description. And for the quantitative analysis tasks, we have 9 of them. So 6 of them are classification tasks. So including to tell if the material is metallic or not, or the magnetic properties of the material. This including 2 properties. One is if the material is magnetic or not, or the second is the material's magnetic order, since there are certain materials as the ferromagnetic behavior or anti-ferromagnetic behavior. So that will be a multi-class classification. And experimental observables, so which means which tells if the material has been experimentally verified. And the directed band gap, which is a key property for to tell if the material is a semiconductor or insulator or metal. And the stability tells whether the material is thermally stable or not. And the last 3 are the 3 regression tasks. One is the energy above all, and the second is band gap and formation energy. Yeah. So this slide illustrate our training approach. We essentially adapting the 2 training approaches. So for the phase 1, we're conducting the representation learning for the bridge model. And for the phase 2, we are conducting the multi-modal instructive fine-tuning with with subtask pair with all the subtask pairs. Yeah. So now let's look at the pre-training stage. So as you can see here in the pre-training stage, we're only including the frozen graph encoder part and the trainable bridge model, because since the bridge model we are using the pre-trained BERT-based weight. So the model inherently has the capability of generating text. So that's why we have so that's why in this case we only want to rely on the bridge model itself to create some like initial text alignment, since the bridge model is able to generate text description as well. So in this case, we only in the pre-training phase, we only train with like 3 description tasks, including the chemical composition, space group, and the crystal system. We're using these three criteria to curating the description text pair text to pair with the certain structures. So in terms of the loss function, it has like 3 terms. So the first term is the correlation function, which is essentially a contrastive loss. So where the in one forward passing function calling, so the bridge model will be called multiple times. When it be called the first time, it will be used for calculating the correlation loss, meaning you are passing the single model input separately, meaning you are passing the structure only data into the bridge model to generating to use the query to extract the structure data, and the second part is to passing the description, the pure text version into bridge model, and then to generating to getting the CLS token for its semantic value, and then we calculating the contrastive loss between these 2 embeddings after the passing through a conversion head to making the dimensionally compatible. So the second one is the second loss is the association loss. In this case, we are trying to making the problems into a binary classification problem, meaning in one forward pass, we will have both positive samples, both positive sample pairs and the negative sample pairs. After so those sample pairs were passing through the bridge model, also generating the embeddings in the representation of the queries, and the queries were passing through one logis head for binary classification to tell if to tell the material if the material text pair is positive or negative. And the third loss is the prediction loss, meaning we're trying to utilizing the bridge model to directly generating the text for us. So that's why the loss function here is the same loss, the cross entropy loss, as we training the pure language the language model. Yeah. So the total loss will be the sum of these 3 losses, and as I said, like in each forward function call, we are calling the bridge model 2 times. One time to calculating the correlation and the association, and another call is to calculating the prediction loss. So regarding the second phase is the fine-tune stage. So in this stage, we're looping every module together, including the frozen graphic encoder, the trainable bridge model, and the frozen LLM. And in this task, we essentially fine-tune the model with all 12 tasks. And the loss function here is also relatively simple because we have multiple tasks. It's very hard to curating the contrastive loss or the negative or positive text structure pairs. So that's why we're just using pure language loss, the cross entropy loss, as the loss of the fine-tune. So in order to show the use or the superiority that the pre-train of the pre-training, so here I'm including a small benchmark comparison where we train the model. We train the matter chat with different training approaches, including one with pre-training, one without pre-training phase, and after that we started doing stage 2 fine-tune, and then we started performing inferences with every 5 epochs. So as you can see, the solid line represents the loss with the accuracy, the arrow of the RMSE arrow regarding the 3 regression tasks, including band gap, energy above all, and formation energy. As you can see, the model with pre-training can have like consistently lower loss and keeps dropping, and as well as and it is also keeps dropping. So like overall, the pre-training shows it proves it's very useful. Yeah. So this slide shows that after the training we perform some like a cross-model analysis to make sure that the two modalities, the graph structure and the text pair are matched. So the left figure is the similarity matrix, where the x-axis is the text embedding and the y is the material embeddings. As you can see, the diagonals has the highest similarity score, meaning it shows a good matching between the two modalities by just embedding level. And we also perform the query usage with some of the text with some of the downstream task where in this case we're using the average of 30. We randomly select 32 material samples and asking the material the same question if the material is thermally stable, and we try to observe like which if the material query like the extracted material embedding is activated or at certain region or not for certain questions. As you can see, like in the middle two column, the two graph shows the mask, the most activated queries when we're asking the stability question. So you can see it clearly tells that like when it comes to a decision-making process, the query number 25 and number 30 are activated. And as for it also shows as the raw value of the average attention value, as I plotted on the right column. So this also kind of like shows that the MetaChat indeed learns the structured information. So this slide shows some result. Here I present some qualitative result where it shows the user AI interaction. So here I'm providing like three samples, and basically I'm presenting essentially all of to show that the MetaChat can generally answer all of the questions that I mentioned before. So for example, the MetaChat is able to get in the chemical structure, chemical formula, the space group accurately for the first material, and also is able to predict the thermal stability of the material as well as the band gap. And as for the middle column, it's able to describe the material in terms of the chemical composition, geometry, and tell the property of if the material is magnetic or not, and the metallic properties of the material, and also predicting the formation energy of the material. And the right columns shows that it's able to predicting the direct band gap and the magnetic order and the energy above Hall. So this is another slide to show that the MetaChat is not only able to predicting the trend task, but it is also able to utilizing the inherited trend knowledge from the pre-trained knowledge from the LLM to answer some downstream tasks. So here we are essentially the left panel shows that the MetaChat is able to answer questions regarding silicon material to giving good reasoning to tell whether why the silicon at certain geometry is not stable. And the middle panel shows where we're using a semiconductor material as an example, gallium nitride. So the MetaChat is not only able to tell the geometry and the properties of the material, but can also providing accurate step-by-step synthesis process of the material gallium nitride. It has all of the substrate and the tools and the temperature and the carrier gas labeled correctly. So yeah. So this slide shows some of the visualization effort that we performed to further analysis why MetaChat can perform, or to demonstrate MetaChat can effectively integrate the embeddings. So here, essentially, we are trying to do some visualization with a certain selected materials. So here we select certain materials, material subset that contains the elements of silicon and carbon. And what we do is first we feed all of the material structures into the MetaChat and getting the embeddings out of the MetaChat's bridge model. And after that, we perform visualization with dimension reduction technique and the clustering. So we're essentially performing UMAP plus the k-means. And in terms of labeling, we are using two metrics to do the labeling. One is the structural similarity, which is where we're using a smooth overlap of atomic position, SOAP descriptor, and to calculating the structural similarity. And we're also labeling the clustering for the sample with the formation energy, which is one of the property of the material. So as we can see here, the left panel shows that is the result that like labeled with structural similarity. So there is distinct clustering between different chemical compositions like silicon and carbon, and also as well as like the same the material with the same chemical composition, but with different geometries, like for example like silicon carbide. So like the middle panel shows is essentially a zoomed version of the left panel, which is an isolated demonstration where, for example, for the silicon structure, it clearly has the low distinction between the low similarity region and the high similarity region. And the right panel shows that like other than the structural similarity, the the embeddings also it has a clearer distinction. It is distinctly clustered by different energy, by formation energy. So it has a it has clear low energy region and higher energy region. So essentially, this this plot, what I'm trying to present in this plot is that the extracted embedding of the MetaChat preserves the structural information of the material, as well as contains some information, some property information. Yeah. So that actually, that drives us to incorporate to the multimodal retrieval augmented generation, multimodal RAG approach, because based on the analysis that we see in the previous slides. So the original approach without the RAG is that like we will have one prompt a structure pair feed into the LLMs, and then we get in one response. And one potential challenge is that like in LLMs there may be like hallucination of LLMs is very common. So sometimes the material, sometimes like the predicted result can be can have like a big variance. It's not very accurate. So like, but since we know that the embedding is extracted from the bridge model from the MetaChat, preserve the structure. So what we propose is that we're proposing a kind of the RAG approach. So instead of having one prompt structure pair, we're utilizing the RAG to to perform a retrieve process from the material database, and this database is essentially our training set. So here we are essentially using the extracted to calculate the L2 similarity between the structure that we want to query and to the material database, and selected at the top two most similar materials. So here, instead of having one prompt one prompt structure sample, we will have three, and then we will have three responses. After that, we perform an aggregation step to generating the final output. So in terms of the aggregation steps, like here for the classification tasks, we're using the maximal strategy, and for the regression task, we're using the average. So here, this slide shows the performance comparison between the or a more quantitative performance comparison across all the material property tasks. So here we're essentially testing across all of the material tasks on the evaluation data set. So here is around we're using around 14,000 materials. So here we benchmarked it with two pure LLMs. One is the Vicuna 7 billion. The second is the Mistral 7 billion. So the pure LLM approach is that we were taking we're treating the CIF structure information as the text, and then along with the question feeding to the LLM to get the answer. And we also benchmarked with three material foundation models, including the ChargeNet, the SHNet, and the MACE, which is the equivariant model. And we're also testing three variant of the MetaChat. The first one is the MetaChat with the invariant encoder. The second one is the MetaChat with the invariant encoder with RAG. And the third one is replacing the invariant encoder with the equivariant encoder. So overall, the top two rows are the classification tasks that I mentioned before. So the evaluation matrix here is the accuracy, meaning the higher the value, the better the performance. And the bottom row is the regression tasks. Here we're using RMSE as the evaluation metric, meaning the lower the value, the better the performance. So overall, like the MetaChat and its variant achieves the highest performance across all of the tasks, and it has especially in the quantitative, like in the regressive tasks, it also has comparative performance to the physical foundation models. So this slide shows some comparative studies where we're essentially testing different LLM architecture settings. So here I'm including 4 of them. So the first one is that we replacing the BERT-based bridge model with a simple adapter, which just doing the dimension conversion. But in this case, we enable the LoRa fine-tuning of the LLM, so that we will have the similar trainable parameters to the ones with the frozen LLMs. The second one is that we were ignored the adapter, just using the pure text version, treating everything as text. But we also enable the LoRa fine-tune, but increasing the rank of the LoRa to make the trainable parameter the same, similar. And we also including two version of the report two version of the MetaChat. One is the MetaChat with the invariant result, and the one with RAG. So as we can see, like the MetaChat and the MetaChat with the RAG continuously outperform both two in all kinds of tasks. And the MetaChat with the help of RAG during the inference can also have slightly boost and more stable predictions for almost all of the tasks. Yeah. So like after that, we demonstrated the MetaChat and its variant in some zero-shot scenarios where we are essentially trying to use the trend model for some newly discovered material data set. So the material data set that we're targeting is the GNOME from the developing from Google in 2023. So like the GNOME is newly discovered and contains the structures that are more complicated than the original material project data. And the bottom rows shows the distribution of the material project data set and the distribution of the GNOME data set in terms of like 3 labels where I'm labeling based on the formation energy band gap and the energy buffer. So the GNOME data exhibit distinct like data profiles comparing to the material project in those 3 targeted properties. So, and here we are trying to using MetaChat with its with different variants. We're testing on the zero shot tasks of the GNOME materials. So like the bottom table shows the overall RMSE loss across across the 3 tasks with a subset of the GNOME data set, because when we perform the inferences, there is only a subset of the data released publicly. So in this subset, the number of the materials is roughly around 15,000. Yeah. So what it shows here is that the meta chat with invariant and the equivariant, they both shows good transferability, zero shot transferability to the new materials. And when we replacing the equivariant encoder module with the invariant module, it was slightly increasing the performance as well. So we're essentially doing the same training, but that only also shows the highly modulated properties of our framework, where we can easily plug in and plug out with the state-of-art modules from both domain in terms of large language, in terms of language models, and also the material properties. Yeah. So here is the conclusions and the next steps. So to summarize, in this work, I introduced the meta chat, and which is the multi-modal LLMs for material property prediction and analysis. And we have then quantitatively demonstrated meta chat's superior performance and some analysis comparing to some other models. And in terms of limitations, so what we observed here is, so here there are still some alignment issue between the graphic-based material embeddings and the language representations. And the second is that the current training set, we're using fixed paraphrase queries, meaning for one certain tasks, we have 10 paraphrase to asking the same question and 10 paraphrase for the same answers. So this may limit the linguistic diversity, meaning meaning we may need more comprehensive textual description to border the range of the material properties and its semantic descriptions. So in terms of future work, one point is that to expand the QA and question and answer pairs, where we can curate in more diverse and task-specific QA pairs to enhance the model versatilities. The second one is maybe we can utilizing the domain-specific fine-tuned LLMs. So there has been articles that people making making specific fine-tuned LLMs on material-related documentations. So then the LLMs are more adapted to the leaning towards the knowledge in the material science areas. So given the fact that our model is highly modulated, we can potentially swap those modules very easily into the model and see and observe if it can improve the performance. And the third one is to testing the material generation ability. Well, two potential approaches, either to utilizing the language generation capability to generating the structure in the text format, or attaching a generative model like a CDVAE or some generative model in material science to directly generating the structure. Yeah, and the fourth point is to extend it to the multi-scale, because the meta chat is focused on the atomic level. As I mentioned, we're also interested in the mesoscale and the circuit level. And we can utilizing the similar concept and to demonstrating the similar frameworks, but with different input format. For example, in the mesoscale modeling, we're probably talking about solving a bunch of PDEs. Then the field information and the text information can be considered as two different modalities, and the similar framework may also be able to use here. Yeah, so that's about it. So yeah, that's everything I have. Yeah, thank you very much.
Thank you, Ying-Heng, for presenting your work. That's very interesting. We can now open the floor for questions. Do we have questions for the speaker? Hi,
Hi
Kyle.
here. Hi. I do have one question. Um, this is Kyle here. I'm from Brown. I have two questions for you. So the first
Mhm.
question being, I was looking at your paper and it says the bridge model includes 32 trainable query vectors. I was just wondering, how did you arrive at this number, and did you observe
Oh,
any bottleneck? For example, if the model, if you use fewer query vectors, would you
yeah.
observe a
Let-
bottleneck where the model start to losing the structural fidelity?
Yeah, I think I have one backup slides here. So this is one of the addition study that we conducted during our revision. So what we observe is like reducing, because like the structure information is quite sparse. So 32 is I mean, the number of 32 is okay. But like what we observe is that like if we increasing the query numbers larger, then the performance will drop. So here we're testing like with four queries. So if we're increasing the query number from double the query numbers from 32 to 64, actually the when we apply the same training mechanism, the performance drops. But if we reduce it like slightly by two to like we didn't observe like a very big difference between eight queries to 8 queries, 16 queries, and 32 queries. But like there's a big performance drops when we increasing the number of queries to the to higher dimension. But we haven't tried the force query. But like there is definitely gonna be a limitation. But like the argument here is like the the atomic embeddings are quite sparse. So like
Yeah.
because like the 32 query length was originally used in the Vision Q&A, because like the framework is adapted from the Vision Q&A work, and the 32 the number 32 queries is originally used for the imaging like data processing. So, but for graphic, the data may be more sparse. So that's why we
Yeah.
observe that reducing it doesn't hurt much. Yeah.
Yeah, that makes sense. This seems pretty curious, isn't it? Increasing the number of query vectors. I thought if you have more queries, they should be able to contain more detailed information, but in reality, it actually um decreases the performance a little bit. This is
Yeah,
pretty interesting, I think.
I think that may have something to do with the limited of data, right? Because
Yeah,
like
yeah, yeah.
yeah, for example, when we train the sequential models, like if we have like very limited number of like sequences data, like typically the conventional like sequence model like LSTM may outperform the transformers. But if we increasing the data
Right.
by a lot, then transformer will have its like a will become superior in terms of performance.
I
So
see, I
I
see.
kind of
That
feel
makes
like it's
sense.
similar here. Yeah, because yeah.
Yeah. Yeah, yeah, yeah. Thank you. I do have another question. So, I just wonder if you freeze the final large language model. I just wonder
Mhm.
if that can be a bottleneck as well. For example, if I provide the whole system with a new material as the input, even though the bridge model can encode the material very well, and the
Mhm.
the LLM can recognize the structure of the material based on your embedded input, if the LM has not seen that new material in its training data before, can it still do analysis on that new material? For example, you have an example where you showed you asked the model, can you provide the detailed step-by-step synthesis for this material? If this material is a completely new, unseen material that is input to the LLM, and the LLM has no prior knowledge on that, would this be a challenge?
Yes, this definitely is going to be a potential challenge. That's something I think that's something I aligned with the limitation that I mentioned with the alignment. So far, what we show, if we eventually reach a perfect alignment, for example, like if you look at this cross model alignment, so there are still like a light spot here, meaning the modalities are not perfectly aligned. So if those are perfectly aligned, then that means most likely meaning the queries are contains a very rich semantic information to the LLMs, then that will enable the LLMs to answer downstream tasks, even with unseen materials. So far, what we have tested is with unseen materials for those tasks that we trained on, it is able to perform it is able to answering the questions I wouldn't say correctly, but you were able to generate the question, right? But with decreased performance. But for the follow-up question, yeah. So currently with the unseen the unseen material, our current approach is probably the working memories, meaning using the multi-modal queries to providing the relative context, and then utilizing the LLMs weight itself and to generating the data to generating the response after that. So that means in the follow-up question, for example, the synthesis question, it may answer the question without having a good structure information. Yeah. So yeah, that's why I said it may have something. It has something to do with the alignment, which can be one next step, as I mentioned, to address. Yeah.
Yeah. Thank you. That's really cool. Thank you.
Thank you, Kyle. Do we have any more questions for the speaker? If not, I thank Yingheng again for presenting his work, and I thank all of you for attending today's seminar. And on that note, have a nice weekend, and I'd like to close this week's Scrum seminar. Thank you.